Today we're going to look at multiplying matrices together. So this is a little bit different than when we were talking about before the addition and subtraction of matrices. If we have addition and subtraction, the two matrices need to have the same dimensions. So just talk about dimensions again. For matrices, we think of dimensions like RC cars, it's rows and then columns. So when we're thinking about rows and columns for multiplying two matrices, the following needs to be true. When I'm multiplying two matrices together, whoops, let's change the color here. I want the columns from the matrix on the left to match up with the rows on the matrix on the right. Now when we do matrix multiplication, it is not commutative, so I can't just swap these two things around. So when I have AB written, it is different than BA. So I'll write it right here, but we're going to see it a little bit more explicitly later on. Is when we're multiplying matrices, A just representing a matrix and B representing a matrix, AB is not BA. So keep that in mind. So when we're looking at multiplying two matrices together, the first thing I need to see is the middle two here, the column and the row, going to match up for me? And if they're not, then I cannot multiply the two matrices. It's that simple. If they do match up, then my new dimensions is going to be the row from the first and the column from the second. So if these two were the same, then yes, I can multiply them. And what are the dimensions for the new matrix going to be? It's going to be this by that. And I'm going to show you an example here. So I'm going to pick a yellow matrix. I'm going to say it's a 5 by 7. I'm going to have a blue matrix. So we already used blue. Let's use purple. Blue matrix is 7 by 3. When I look at this, I'm looking at it and I'm saying, okay, are the two inside here the same? I have 7 and 7. Yes. So since they are, I can multiply these two matrices. When I do multiply them, I write it as ND, it's just short for new dimension. The new dimension of the matrix is going to be a 5 by 3. Take my rows from here and my columns from here. And you'll see how we do matrix multiplication in a minute, but we're just first covering what it's going to look like and if we even can do it in the first place. Now, if I were to reverse these two things and write a 7 by 3, and I am multiplying that by a 5 by 7, I would see from the inside here that they are not the same. Nopers, Michael, can't do it. So when I see that, I just say I cannot multiply these two matrices together. So again, AB different than BA. So when we're looking at this, we are going to go through a couple examples here. First one here is we have matrix A defined as a 2 by 3 matrix, and then we have matrix B here defined by a 3 by 4 matrix, and we're going to see, can we multiply these two things together? Well, the first thing I want to do is I want to match the inside. So here I got 3 and 3, check, that looks good to go. And now I want to name the dimension, if it's possible, for the new matrix. So we just said it is possible. The new dimension here is going to be a 2 by 4. So when we're looking at this, again, we're taking the rows from the first one, columns from the second, and that's our new matrix dimension. When we look at the next one here, we've swapped them around a little bit. So here I've got AB is a 3, 2. I have B as 3, 4. The first thing I want to look at is, do these match up? They do not. Nope, can't do it. Cannot multiply those two matrices together. So next here we're going to see just another example here for the product and how we actually go through and multiply these things. I'm going to do my very best with colors here to highlight exactly what's going on. Just keep in mind that the first couple that you do seem weird and it doesn't seem like it totally makes sense, but we're going to try and take it step by step, keep it nice and easy. What I'm going to do is I'm going to first look at the dimensions of my matrix. So my dimensions of the matrix here, rows by column. So I have 1, 2, 3 rows by 2 columns. 1, 2, just like that. For my second matrix here, I have 1, 2 rows by 2 columns. The first thing I always want to do is check to see, can I multiply these things? Yes, I can. Whoops, not a very good check mark there. There we go. Yes, I can. And then what will my new matrix be? My new matrix will be a 3 by 2. So I'm going to write ND. Going to be a 3 by 2 matrix. So when I'm looking at actually doing the multiplication, what I'm going to do is I'm going to take the first row from my first matrix, and I'm going to multiply it by the first column of my second matrix. And now the way this works is the first thing in the row here, the most left, goes to the top thing of this column here. -2 times my -1. So I'm going to write it out here as -2 times my -1. And then I'm going to say plus, and I'm going to do this for each of these different elements. So now I'm going to do it for the 3 and the -2. So now I've got 3 times -2 here. And I'm definitely going to run out of space here and get a little squish, but I'm going to do the best I can. But I'm going to summarize our totals down below here. So I'm going to jump to a sort of like middle answer, and then I'll jump to my final answer here. So we'll put a little equal sign there, equal sign here. So I want to take the product of these things. We'll have this be our nice huge one here. So -2 times -1 gives me a +2. And then here, well, I'm going to actually simplify. So I got 3 times -2, which gives me -6. So when I'm adding a -6, I'm just going to say -6. And then I say, okay, well, what is 2 minus 6 gives me -4. So I've done now this first row, first column position. I'm going to do the next one. So the next one I'll do in red. I'm going to do first row, second column. So now I'm doing the -2 with the 3 here. Hopefully it's clear that these are separate things just because I'm using different colors. There's not an awesome space in between there, but I will run out of space otherwise. The next one I'm going to do is the 3 going with the 4. I'm going to add these things up. So here we get -6. And now I'm going to say plus 12. And when I add this together, I get 6. So I'm giving myself plenty of room now. The vertical will be the issue for me here, but we'll do our best. Let's see, we'll use blue for the next one. So I've now completed my first row. I did my first row times all of my available columns. So now I move to the second row. So now I have 1 and -4 that I'm going to multiply by -1, -2. So let's write it out in my 1 times the -1 plus my -4 times my -2. Add these things up. So I have -1 plus 8 gives me 7. I'm definitely going to run out of room here a little bit, but we'll just make a little bit extra there if we can. Next one here is going to be in purple. So I'm going to do my row to the second column. So now I've got 1 and 3. Plus now I've got my -4 and 4. So 1 and 3 gives me 3. Plus now I've got a -16, so I'm going to say minus 16 gives me a -13. Next one here, doing a lighter purple color. So I have 6 and 0 times my first column here, the -1 and the -2. So once you do a few of them, hopefully it starts just becoming a little bit easier as we go through. And we see a consistent pattern here too, right? So here's -1, -1, -1, -2, -2, -2. If you want to keep consistently writing it in the same order, it helps kind of like organize your thoughts there. And then I'm going to add these up. So I get -6 here. And I'm adding a 0, so that's nothing. Stays as -6. And now for my last one, we'll do this kind of light brown color. I have 6 and 0 going with my second column here. So now I'm doing 6, whoop, kind of wonky there, 6 and 3 plus 0 and 4. Pretty easy with the zeros. We get 18 plus 0 gives me 18. So our beautiful multicolor answer right here for the final product of these two matrices. So again, taking row by column and adding it up in that position, row by the next column, adding it up in that position. Once I've completed the top row, I move to the next row and continue moving on. And I always want to make sure that it matches with what my dimensions should be. So a 3 by 2, this is a 3 by 2. Perfect. We win. Next here we want to find the product of two matrices. We have matrix A and matrix B. What we're doing here is we're just highlighting the difference between this and this. Okay, so again, like I said before, AB is not the same thing as BA. So the first thing we do when we multiply two matrices is I want to look at their dimensions. A is a 2, 2. B is a 2, 2. So when I'm going to multiply these things, AB and BA are both going to match up in the middle, perfect, and they're both going to give me a new dimension matrix of 2 by 2. So I'll just jot that down for both of these. Whoops, it's going to be a 2 by 2. If they were different, I would write them down twice, but since it's the same, I'm just writing it down once. So let's start with the first one here. So AB, I'm just going to highlight in colors here the solution. That way we'll save some time. It is nice to have everything written like this with all the colors and everything, but once you see it once, it kind of is just repetitive if I do it again and again. So I'm going to start underlining things. So the first thing I'm going to do for AB is I set these two up. I'm going to do my first row by my first column. And actually what I'm going to do, before I even do that, is I'm going to grab these using my clever Microsoft Paint skills here, and I'm going to throw them over here. That way I can write it out twice, once for our AB and once for our BA. So we'll jot down the AB, AB multiplication part here. And then we'll do the BA multiplication part here. And you may be thinking, Mr. G, these are swapped on the bottom. You haven't arranged them correctly. No fretting. We'll get there. Much better. So let's step through it now. I want to do my first row by my first column, and that's going to give me this 7 here. And I'll write it out just a couple times because we're still kind of new to it, so I'll probably do the top one out, and the next one I'll just kind of like talk through it. So I have 3 times 1, and I'm just adding these up as I go. So instead of writing 3 times 1 and then 2 times 2, why skimp, right? I'm here to teach you. Might as well just show every step. People want to see all the steps. We'll do all the steps. I'll do it one more time. After that, then I'll start skipping on the next one. So let's start writing this thing out. So we'll have a 3 multiplied by a 1, and we're adding that to a 2 and a 2, which gives me dun, dun, dun. All right, so I get 3 plus 4, which is 7. Sweet. And that's how we get this 7 right here. So let's look at the next one. We'll do it in orange. I'm going to do again the first row, but now I'm doing my second column. So I'm doing 3 and negative 4. And then I'm going to add my 2 and 1. So 3 and negative 4 is going to give me negative 12. and then I'm going to add my 2, which gives me negative 10. Next one here we'll do in yellow. We're going to do, no, yellow doesn't work because it doesn't underline well in the white area here. Second row, first column now. So I've got my negative 1 times 1 plus my 0 times 2. I'm going to add those up so I get negative 1 plus 0, which is just negative 1. And then my next one here, negative 1, 0, and the negative 4, 1. There we go. And so now I've got negative 1 times negative 4, which gives me 4, plus 0, which is 4. Perfect. So that is how we are getting each of these entries right here, which match up perfectly, which is exactly what we want. And we now have our product. So this is A, B right here. For the next one, I'm just going to talk us through how we're getting each one of these things. So audio good, visual will be a little bit lacking here. So as I look at the first one here, I've got, okay, my 1, negative 4 by my 3, 1. So here, I know I've got 1 times 3 is 3, 3, and then I've got 4 times negative 1, excuse me, negative 4 times negative 1 is 4, 3 plus 4 is 7. I guess I'll do like 2 intermediate steps, that way we're getting to the point where we can jump to the conclusion, but we'll write it out. So 3 plus 4, 7. Next one, same row, second column. Here I got 1 and 2, negative 4, 0. Typically I wouldn't even write the plus 0, but for illustrative purposes I will. Next one here we have our second row, first column. So 2 times 3 is 6, 1 and negative 1 is negative 1, gives me 5. And then my last one here is my second row, second column. So here I got 2 times 2 gives me 4, 1 times 0 is 0. There we go. And we see this matrix is definitely different than this matrix here. There are some instances where maybe the two will be the same. We'll talk about that, and that's a different aspect than what we're looking at here. In general, AB and BA will be different matrices. So again, not commutative. For using our different matrix operations like we were looking at before, like we have scalar multiplication and we have our distributive property, it holds true for each of these. Now again, I'm going to talk about the way that I would show you how to do it and how I would do it because, again, please don't tell anybody, but I'm incredibly lazy. It just comes off as smart because I'm effective in what I do. So when I'm doing this thing, I'm thinking, okay, I can do one of two things. I can do the B and the C added up first, and then I would do A times that thing. I'm just going to write it as junk. Okay, so A times this junk matrix here, and I'm good to go. In doing so, I will have done my addition step once, and I will have done my multiplication step once. So just keep that in mind. If I were to go the route of distributing this A into the B and into the C, it would look like AB plus AC. When you're doing the scalar multiplication, it stays consistent with whatever side you're multiplying to. So we're going to talk about this a little bit more later on, but matrices have left matrix multiplication and right matrix multiplication. If I wanted to multiply the A on the right, I would have to actually write the A over here. So rather than that just be an abstract thing that I mentioned, I'm just going to explicitly write it out. So if I had B plus C times A, it gives me BA plus CA. Different than if I were doing it from the left. Okay, so A times B plus C gives me AB plus AC. If I did B plus C times A, it's going to give me BA plus CA. So just keep in mind they're two different things. So jumping back into this now, if I were to do this step, what I'm essentially doing is I'm doing the matrix multiplication for 2, right? So I'm going to do AB and I'm going to do AC, and then I'm still going to add that stuff together. So we'll say I get a thing, and I add it to a blob, right? So when I'm doing this, again, just keep in mind, I've done my matrix multiplication step twice now and addition once, versus here I did addition once and matrix multiplication once. Again, this is the route that I would choose. This is totally fine. Perfectly acceptable. If you do this, you get the right answer, assuming you do all the right steps. So I'm going to quickly walk through this here because that's the whole concept trying to be displayed here. So when we look at the first one, we are going to add these two things up. When we add two matrices up, just keep in mind again, they need to have the same dimensions. All of these are 2 by 2 matrices. We can add them all up and we can multiply them all. Cool. So 2 by 2 and a 2 by 2. Negative 2 plus my 1 gives me my negative 1. 0 plus 1 gives me 1. 4 plus 3 gives me 7. 2 plus 2 gives me 4. Boom. That is where this matrix is coming from. This one just being carried down for fun until now I'm going to do my matrix multiplication. In the matrix multiplication step, again, just keep in mind, I'm not going to do all these written out because it's just the same thing we've done before, but row by column to give me this entry, right? 2 times negative 1 is negative 2. 1 times 7 is 1. Negative 2 plus 7 equals 5. That's how I'm getting this first entry. And it follows for the rest of the matrix multiplication. Since we've done it a couple times, I'm going to leave it as that. This one is done. So if I do A times, and in parentheses B plus C, I will get this matrix of 5, 6, 22, 11. If I go the route of looking to do my matrix multiplication twice, so I'm doing A, B, and I'm also doing A, C, which is here and here respectively, I'm going to be doing my matrix multiplication for each of these steps. Here again, I've got row by column here. I'm just going to display once. 2 by negative 2 gives me negative 4, and I have 1 times 4, which is 4. This is going to add up to give me 0, which we see here. I'm going to also do it over here, just to show you one of them. Row, column, 2 times 1 is 2, plus 1 times 3 is 3, gives me 5. There we go. When we do this, oops, sorry, circled the wrong 5 there. When we do this, I now get two matrices that look like this, right? This is thing, this is blob. Now I'm going to add those together. 0 plus 5 is 5. 2 plus 4 is 6, etc., etc. Note, and this is the big takeaway from this problem here, what's the color we haven't used yet, this gray thing, that this matrix is the same as this matrix. Coincidence? I think not. All of our matrix operations holding true here. So the conclusion is that we can do it this way, or we can do it this way. They are equal. Here's a summary of those multiplication properties here. So as we look at it, we have the associative property. Keep in mind that now we have explicitly written left distributive property and right distributive property. This is exactly what I was talking about before right up here, is when I said, okay, we've got A on the left being distributed into this, looks like this. If we had it on the right, it would be different. It would look like this. Well, that is exactly what we have right here. So just keep in mind, again, we have left matrix multiplication and right matrix multiplication. So by saying something is AB or say something is BA, they're two completely different things. Keep that in mind. With our scalar multiplication, it doesn't matter which we do that scalar to, just make sure you're not doing it to both of them. So if I had a scalar on the outside and I was multiplying it into a matrix multiplication problem, I'm just want to keep in mind that this lowercase c is meant for like scalar multiplication. It's confusing because the uppercase c is used right here. We kind of like would almost prefer there be some sort of like k or something. That way it's a little bit more separated, but just keep in mind that c is a scalar here. So this is like if I said 5 times and then I had like, you know, whatever my A and B matrices are, we'll say matrices, excuse me, 1, 2, 3, 4, and I don't know, 5, 6, 7, 8. So original, Mr. G, so original. So if this were the case, I have one of two options. One is I take the 5 and I multiply it to the first matrix, which would turn it into 5, 10, 15, 20. And then the second matrix, second matrix just stays the same. And then we would actually go through and multiply these things. Or I could do the same thing, but instead take the 5 and go to this matrix right here, and that would be 25, 30, 35, 40. And I would have my original 1, 2, 3, 4 here. When we do the multiplication for these two matrices, so I'm going to say like equals check mark, equals check mark, they will be the same thing. So again, it doesn't matter which you choose to distribute to, it's going to be the same. And that's what this is displaying for us right here with that scalar multiplication property. So here we're actually going to get to an example of like where we would use this thing in real life. So I mentioned this in class that we have matrices that are involved in all like the computer graphics and things we do, or we're doing all this like vector manipulation and stuff like that in the background. So we enjoy matrices all over the place, but we don't always know exactly where they're going to be applicable to us. Here's just another application. So we have like an inventory of things and a cost per item, and we're looking at the total cost matrix. So again, we'll separate this for this example. We're going to be using women's and men's baseball and softball teams, and we have a number of items for the team. So we have bats, balls, and uniforms, and we also have a cost associated for each of these things. So I'm going to try and keep it all on one screen as best I can. I'm going to kind of flip back and forth here. So we'll say we do women's bats in red, bold, and we'll do the balls in a red squiggle, and we'll do the uniform in a dash. So I'm going to flip down here. For the women's team, we see that we have 12 bats, 45 balls, and 15 uniforms. For the men, sometimes it's so hard to get that to work. For the men, we'll do the same thing. We have bats, balls, and uniforms. So here we're going to have our bats, our balls, and the uniforms. Now, when we're doing the matrix multiplication here, we want to multiply by the cost for these items. So we have each bat cost 21. We have each ball cost, oops, I should stick with my squiggles here. Each ball costs 4, and each uniform costs 30, and that's the dollar amount right here. So we have our bats, our balls, and our uniforms. So when we're setting this matrix multiplication up, you could orient it the other way as well. So like if you wanted to use bats, balls, and uniforms for your rows, and then men's and women's for columns, you can do that. And then for dollar amount, it would just be dollar on your rows, and then bats, balls, and uniforms for your columns. Either way is totally fine. They just need to match up. So the first thing we check is we look at the dimensions here. We have a 2 by 3 matrix, so we make our cost matrix a 3 by 1 matrix. Again, if you wanted to flip these two things, which can be applied for some other problems, we could. So just keep in mind that it's got to match up with whatever you've got. So looking at this problem, we're looking at like the equipment themselves versus like the total cost of the team. So this is how we want to orient the matrices here. So jumping down to look at some of the multiplication going on, I'm going to highlight it as best I can for you. So here we have the women's, I should try and, well, I'll do the best I can. So there's going to be some overlapping of these things, but here's our, oops. Here's the artistry test. Can I maintain all of these little cues that I've done so far? Let's try my best. There we go. Do the men's team real quick here. We got 15, 38, 17. Again, we're doing row by a column. So red thing times, now I'm doing my orange thing. So I'm going to put it on the side here. So this is my bold squiggle, not a very good squiggle, and then my dash. So here I've got bold squiggle dash and bold squiggle dash. Hopefully that's at least semi-legible. This is probably the worst one. So now I'm going to actually total all these things up. So product here plus the product here plus the product here gives me 882. And I'm going to do my 1521 plus my multiplication here plus my product here, and it gives me this 977. So this is the total cost per team. So the women's team requires $882 worth of gear, and the men's team requires $977 worth of gear. So just another example of how matrices can help us in real life, and that is the end of 4.2.